Good morning, everyone. I'm Zheng Kaixu from National Central University in Taiwan. Welcome to the AOGS-RAC LLWG online seminar series number 11. So today we are delighted to have a special guest with us, a standout expert in space science, Dr. Douglas Rowland. Dr. Douglas Rowland graduated from the Caltech and later earned his PhD in physics from the University of Minnesota. After completing his study, he conducted research at both the University of Minnesota and the NASA Goddard Space Flight Center. Currently, Dr. Rowland is over at NASA Goddard, heading up a laboratory that's all about Earth's upper atmosphere. He has a particular passion for studying our planet's upper atmosphere and the space weather. But Dr. Rowland is not just a scientist. He has been involved in and led numerous space missions. He once headed a CubeSat mission called Firefly, which successfully operated in space for 4 years. And now Dr. Rowland is in charge of an exciting project called the Geospace Dynamic Constellation. So today, Dr. Rowland will give us a brief introduction for this project. So all right, let's not waste any more time. Let's welcome Dr. Douglas Rowland. Dr. Douglas, please.
Thank you so much, Dr. Kai. I appreciate it so much. And thanks again for everyone's patience as I got my screen sharing set up. As you heard, I'm here to talk about NASA's next strategic mission in the ionosphere thermosphere, Geospace Dynamics Constellation. And I'm very excited to be here to have that discussion because it's a product that's been in the works for many years. It really got started a few decades ago with some concepts. And then in the 2013 decadal survey where NASA seeks input from the community about the science that should be done, this mission was the highest recommendation for a large mission in the ionosphere thermosphere. So since 2013, we've been trying to get it moving. And in 2019, the NASA headquarters issued a report. It was a science and technology definition team report that outlined the science the mission could do. And then we began our study. And I'll go through some of the history, but basically we are now in the first of 5 phases of the mission. This is phase A, and phase A is the preliminary design initial concept phase, when you make sure that you have the science objectives you need, the requirements of the system to do the objectives, and that you can scope out the cost and budget and schedule. When we have completed this phase A, we'll be in the preliminary design phase, then the comprehensive design phase, then and then building things, integrating them, testing them. And then phase E is when we are doing science on orbit. So we're in the first of 5 phases. As you can imagine, it is a long project. The silver lining of that is that it gives us time to have these conversations throughout the world. I think you'll see that GDC is uniquely suited for international collaboration in science, similar to the Cosmic Mission and some other ones that we are so familiar with from your groups. GDC has this global reach. The science it can do is global, and it really benefits from partnerships with people around the world. So in a way, having a 10-year start to finish, in order to get to launch, is good because it gives us time to set up some partnerships and some collaborations. And then when we launch, we can really maximize the science return from this mission. So as you heard, my name is Doug Rowland. I'm the project scientist, and that means that I'm responsible for coordinating science on GDC. We have a very large science team of 100 individuals. Each instrument has a principal investigator. There are 6 instruments, and they have teams of co-investigators and collaborators. And then we have interdisciplinary science teams also. So I'm just representing a very large group. This is not my work. This is the work of many people. And then aside from the scientists, we also have a very large engineering and technical team, management team, to actually build the satellites and make sure that they work the way they're supposed to. So I'm just representing the team here. There's a very large team behind me. Okay. And if you have questions, I don't know if you prefer to put them in the chat or how does that work, but you feel free to, as whatever your custom is here, and we'll just make it work. Okay, so many of you, obviously, if you were in this working group, you're familiar with solar terrestrial physics. I included this slide for a different audience, but I liked it, so I kept it here. And the reason I like it is it really shows 2 different perspectives on the sun and the Earth. And the top 2 are perspectives you might have if you're a regular person who doesn't study space science. You might think the sun is kind of a featureless ball that gives us light and heat and energy, but doesn't change very much. And you might think the Earth is mostly dominated by people and maybe weather, like clouds, terrestrial weather. And when you get into the solar terrestrial, we're focusing on these other ways of seeing the world in the sun. And on the bottom left, you can see the sun in hydrogen alpha, and then a white light coronagraph picture superimposed. And that shows that the sun is not featureless in the ultraviolet and the X-ray. Of course, it's very structured, and there are lots of regions where magnetic fields are converting energy into kinetic energy and heating and accelerating plasmas to very high energies. And some of those plasmas, of course, stream out towards the Earth in the solar wind, and then transfer energy through electrodynamic and kinetic process to the Earth's magnetosphere and ultimately to the atmosphere. On the bottom right also shows some dynamism in our Earth's atmosphere. That's a picture of the aurora from the International Space Station, and the aurora are a very beautiful and visible symptom of this interaction, this almost invisible interaction between the sun and the Earth. You can see it when these electrons that are accelerated in geospace are accelerated down into the atmosphere and form these dynamic shapes and patterns, and really give you an idea of how much energy is being transferred into the upper atmosphere. So that's the regions we're studying, the solar terrestrial connection. And what I just put a little summary slide here just for your input. And of course, if you like, I can send these slides afterwards if anyone has detailed questions. But when we say the Geospace Dynamics Constellation, GDC, it's a decadal survey recommended mission. It's currently being studied for the Living with a Star program in NASA heliophysics. So Living with a Star is my favorite line of NASA missions. It's the part of heliophysics that studies fundamental science, but with applications. So it has a component of it which has to do with targeted research that will help us understand the space environment. Oops, can't seem to get rid of my chat window. I don't know if it's blocking you guys or not, but I have this chat window in my screen. I can't seem to. So sorry, I had a little obstacle there. So Living with a Star is the program that provides fundamental science, but with an applied purpose. In other words, we want to study things because they're science interests, but also because they affect society and technology. And so this is an area where we typically look at various aspects of the science behind space weather variations. GDC happens to be orbiting in the region that is the heart of space weather interactions that directly affects our human societies. We have things like radio frequency scintillation. We have aviation level radiation effects. We have ground induced currents. And we have orbital drag on satellites, spacecraft charging, and so on. And I'll describe those later, but ultimately our mission is not a space weather mission, but we are studying the phenomena that can be used to further predict and improve models of space weather. So that's what Living with a Star is all about. A GDC is a low Earth orbit, so it's at 350 to 400 kilometers and high inclination at 82 degrees. It's a constellation of 6 identical satellites. And what we always like to say is provide the first global picture of the upper atmosphere and its responses to forcing from the magnetosphere. We've had pictures in a sense of the upper atmosphere before. We've had auroral imaging missions. We've had the cosmic missions have been very successful at providing 4-dimensional measurements of the variation of ionospheric plasma in regions around the Earth. But what we're lacking in those areas is maybe the neutral gas measurements and various other measurements that can provide the comprehensive picture. So in reality, what we need is auroral imaging and cosmic and GDC and several other missions and ground-based observations in order to really provide the complete picture. But I think GDC fills some major missing gaps in that picture, and I'll talk about those in a moment. And so by having these 6 identical satellites, that's something that we've been doing for a while with the cluster, as a community, cluster, swarm, MMS, a number of satellites a number of missions that have multiple satellites that they use to distinguish spatiotemporal variations and to look at longitudinal and local time variations at the same time. And using 6 satellites is very key to GDC as well. So it's in this region that's of high interest space weather. It uses 6 satellites, and it's comprehensively instrumented to provide this first global picture and systemic research of the upper atmosphere and its responses. The prime mission is 3 years in duration. We carry propellant for at least 2 additional years. So we hope to manage that propellant and use it in such a way that we can get a very long extended mission. But of course, we can't guarantee that because we're only really designing it to last for 3 years. Often the spacecraft lasts for many years longer than their design life, though. So we want to take advantage of that. We had been planning to launch in 2029. For budgetary reasons, we've now slightly delayed that launch. We still don't have an exact launch date, but we're expecting it to launch in the early 2030s. So as we plan, potentially international partnerships, or as you plan science that you want to do, that's really the time frame you should be thinking. We're not going to be launching this certainly before 2030, and early 2030s is probably the best bet at this time. We'll know in about 2 or 3 years what our exact launch date is. I'll be sure to share that with you. We are going to provide, even though it's not a space weather mission, we are going to basically serve as a pathfinder by providing real-time space weather observations in the LEO environment. We're going to provide measurements of neutral density, orbital drag, electric and magnetic fields, electron and ion precipitation, and all the neutral and ionospheric gas motions and distributions and composition and temperature. We also have GPS-RO instruments on board of the same family as those on Cosmic, although ours are at a lower altitude and maybe will not be quite as capable in that sense, but they're going to be very exciting, I think. We are definitely, I think the bottom line is the most important. We're really seeking international partnerships and collaborations. These could range in any different way, from scientific collaborations, or if you have complementary observations you're planning, or complementary studies or model development, research that you're doing with Cosmic and other missions we could learn from for GDC. That's certainly very valuable. But I'd really like to just open that discussion up at the end of this talk and start that discussion so we can look for areas where we can partner. So this is NASA's heliophysics fleet. We call it the Heliophysics System Observatory. And you can see there's a lot of missions. It's supposed to study everything from the sun, the solar surface, or maybe even a little inside with the solar interior, all the way out to the heliopause. And so the missions that are in blue are ones that are currently flying, and the ones that are in yellow are the ones that are in development. And one thing you might notice is that the ones that are in development, we have Tracers, EASY, GDC, and Helioswarm, and Escapade, and several others. All of those are multi-spacecraft missions. So there are valuable things you can still do with single satellites. I think the JAXA is launching Solar C, and we'll have the UVST telescope on there. We're launching MUSE, which will be another solar telescope. Oh, and Punch is another one. Punch is another one that has 4 satellites. IMAP will be a single satellite, but you can sort of see that a lot of our science topics, not all, really depend on having multiple satellites in order to either get better coverage or have be able to tell spatial and temporal variations apart from each other, or just to get better spatial distributions of phenomena. And that's a pretty common theme coming up in NASA heliophysics. So GDC is here, be measuring sort of the heart of the system, where ultimately the energy from the sun, all the energy from the sun is dumped in 3 different ways: the direct ultraviolet and X-ray illumination, magnetospheric energy, and then also solar energy that's reprocessed in the lower atmosphere and then propagates back up. So I'll talk about those in a minute, but you can sort of see GDC is at a crossroads. It's sort of where all the different phenomena come together and provide really interesting physics. So the focus of GDC is how does the global ionosphere thermosphere respond to magnetospheric energy input. And the reason we care about this region of the ionosphere thermosphere between 300 and 400 kilometers is that's the region of strongest coupling. You have coupling between ions and neutrals. Above those altitudes, the ions really dominate. The ionization fraction becomes very large, and most of the phenomena are driven by electric and magnetic fields. At lower altitudes, the neutral gas dominates, and pressure gradients and wind really dominate a lot of the chemistry, dominate a lot of the dynamics. In this region in between, you have this really strong and interesting coupling where sometimes the ions are in control and they drive the neutrals. Sometimes the neutrals are in control and they drive the ions. And there's sort of a trade-off, a back and forth as they experience their own phenomena. So this region, for those who aren't familiar, is right below the International Space Station, which is at about 400 kilometers. GDC will probably be in mostly the 350 to 400 kilometer corridor. I meant to update this slide, but 350 to 400 is a narrow slice, and we want it to be narrow so that we can readily accumulate lots of data at the same altitude for future comparisons. On the right is an animation made by Darren Dezeu at NASA's CCMC, inspired by some animations that Ilka Dornbos has made. And what you're looking at is the temperature from a model, from the TIDE GCM model, in the Earth during a simulated geomagnetic storm. And yellow temperatures are hot and purple temperatures are cooler. And you can kind of see all this dynamic fluctuation, and where the temperatures at the pole are high because that's where the energy is being deposited, the time varying magnetospheric energy. And then over time, that heat and the heat flux, it gets transmitted into various ways to low and mid latitudes. And you can see that again as it starts again. And what's represented in the colors, the temperature, the pressure height is exaggerated here. So you're seeing a contour of constant pressure, but its variations are exaggerated by a factor of 10. So that's sort of showing the exaggeration there. But I think it's really interesting to show how dynamic this region is and how much the variations depend on time, latitude, and local time as well as longitude. So then, what I'd like to say about GDC is it's going to revolutionize, I think, our understanding of the upper atmosphere, the ionosphere. And I liken it to the difference between our first television picture from space on the left. That was from the TIROS-1 satellite in April of 1960. We'd had some sounding rocket and balloon images from near space or the edge of space, but those were brief. TIROS was the first satellite that would let us track weather systems and try to understand where they were moving from and where they're moving to, and look at the dynamics of storms and clouds and things. And that was where we started at the beginning of the space age in 1960. And on the right is where we are today. That's just one particular data set that we have from the NOAA GOES satellites, the Geospace Stationary Operational Environment satellites that measure weather. And that's a hyperspectral image. You can see many details in the colors and in the various features there. And people who study lower atmospheric meteorology, that would be a major data set for them, because they can now really comprehensively measure the system and then use that to test their theories and to explore how the models can be improved to get better and better representation of reality. So we've gone in 62 years, we've gone from the left picture to the right picture, and it's just a revolution. Having this much data in the lower atmosphere lets you do data assimilation and have really high fidelity models. And we're not there yet in the heliophysics world. We're probably several decades behind, where we have our data sets are too sparse typically to do the very large data assimilative models, but we're getting there. And I would hope, my hope is that in 20 years, we will show similar kinds of change for how we understand the upper atmosphere based on GDC's science. So here, as you know, the ultimate energy source for weather is the solar, visible, or infrared radiation. I'd like to contrast that with this picture. This picture shows an artist's conception of the upper atmosphere and ionosphere. The reason we don't have a picture is because there are no pictures, no global pictures that show all the processes. We have pictures of air glow, we have pictures of the aurora and so on, but we can't easily measure, take pictures of magnetic fields. We can't take pictures of neutral gas temperature, for example, things like that in general, at least not on a global scale. So what we've done is we've indicated, this is a figure from Joe Grabowski that indicates the different phenomena that happen just schematically. And the most important thing to notice is that, first of all, the upper atmosphere is very segmented by high, low, and mid latitude. And the reason it's segmented is because of the magnetic field. A lot of those interactions from the magnetosphere come in the form of field-aligned currents and currents and the flow there. And those are typically at high latitude, where the interaction with the solar wind is very strong and the magnetosphere can send lots of energy in. That same magnetic field limits a lot of the plasma phenomena from directly affecting the low and mid latitudes. Except there are several processes that can do that. And we'll talk about that as far as our science objectives. Things like traveling atmospheric disturbances, penetration electric fields, disturbance dynamo winds, and so on. There are many, mostly neutral, but not entirely neutral mechanisms that can carry that energy outside of the high latitude region and really drive dramatic changes in the low and mid latitude. And that's the purpose of this working group, as I understand it. And so I'm very happy to show that GDC will provide the exact kind of data that would be helpful to your studies, I think. And we'd like to collaborate with you on and learning what you're doing. So in this picture, unlike the previous picture where the solar, visible, and infrared light was the main energy source, here we have three energy sources. And again, ultimately, they all come from the sun, but we really are distinct enough that we separate them into three. We have the direct EUV and X-ray forcing. Those emissions are absorbed preferentially in the upper atmosphere. They ionize the upper atmosphere to make the ionosphere, and they heat and change the composition of the upper atmosphere. And that will be measured primarily by existing missions and ground-based measurements. We have the timed and SDO missions currently measuring those things. We have the GOES mission. I'm not sure if Solar C will have X-ray spectrometer, UV spectrometer, but there are a number of missions that have been proposed to do that in future. and GOES will certainly provide a good solid measurement of it. Then we have the magnetospheric particle chain, which is number 2. And that's the one that GDC is going to focus on. It's really the 2 kinds of inputs. We have electromagnetic energy in the form of field line currents and Poynting flux that can drive currents into the atmosphere and change the plasma motion in the ionosphere, and then also affect the neutrals by collisions. And then we have kinetic energy, which is electrons and protons and other ions being accelerated right in the magnetosphere and shot into the atmosphere, and that can heat, ionize, and change the chemical composition of the plasma of the gas in the atmosphere. And GDC will focus there. And then the third chain, which a sister mission, dynamic, will focus on, are the dynamical, chemical, and electrodynamical inputs from below. So these are lower atmospheric forcing, like tides and planetary waves and gravity waves. And they're very interesting. And I think we can't really understand the whole system without dynamic. But the combination of GDC, dynamic, and good measurements of what's happening in the sun will fully characterize, I think, all the energy sources and let us really understand these different distributions. So GDC has 2 science goals, and I'll show you the objectives shortly. But the first science goal is what is the high latitude response of the ionosphere thermosphere to magnetospheric forcing? So that's response in terms of plasma density changes, neutral wind driving, and neutral density response. And then the second goal is what are the internal processes that take this high latitude energy and momentum and globally redistribute them and modify the subaurora, the mid latitude, and low latitude areas. And those are fascinating processes, very complex, and I think GDC will help contribute a lot to that goal as well. I can't see the chat window, so if anybody does raise their hand, I'll just ask you to maybe let me know verbally if you can. Just briefly, we have these three groups: the solar variation. Again, we're talking about the EUV soft X-ray. The visible light varies only by 0.1%, so it's very small variation. But when you look at the EUV or soft X-ray, it can vary by 10 to 100%, depending on the 10 times to 100 times, depending on the wavelength. You can see in the left sort of a solar min, solar maximum, and solar flare condition, like a spectra and X EUV and FUV from Mitchell et al. 2020, and you can see the variability at different wavelengths. On the right, you can see what that impact is on the upper atmosphere. The altitude in kilometers is the vertical scale, and sort of where the colors start, that's about 100 kilometers. That's about where the beginning of the EUV absorption is in altitude. And what you can see is the EUV spectrum there in white, and then the corresponding modeled density, the temperature of the energy deposition, I guess is the color, energy deposition of EUV or X-ray that wavelength in the atmosphere, and also where and what altitude it's deposited. So you can sort of see different wavelengths preferentially deposit energy, different altitudes, and different wavelengths have different efficiencies of depositing energy there. So those 2 pieces kind of really show you how variable, if you vary the sun, if you have more F10.7 or more variability or different structure in the spectral changes, you'll get very different responses in the ionosphere thermosphere. And that's very important. But GDC is not directly measuring those solar fluctuations. We're measuring the response, and we're relying on other missions to measure the UV and X-ray spectrum. And I wanted to point out that the total solar radiance impinging on the Earth is about 173,000 petawatts. A small fraction of that is in the EUV, only a few petawatts. And just for context, the maximum solar wind power is about 15 terawatts. So that's the scale. But the reason we care about magnetospheric energy is because it's localized, it's bursty, it's episodic. And so if you want to understand the global atmosphere, you need to understand the sun. But if you want to understand what causes local phenomena and what drives dynamic phenomena, that's the magnetosphere and the lower atmosphere. So the magnetosphere, you can see that in effect here. This is a nice animation by Ilke Dornbos at TU Delft. On the left are Gonglu has a simulation as AMI electrodynamics based on the ESA swarm mission, measuring magnetic fields, and they infer field line currents and Poynting flux and electrodynamics. On the left, you can see the yellow trace is the swarm satellite coming over the pole every 90 minutes. And in response to changes in the IMF, the interplanetary magnetic field, the field line currents intensify and more energy is dumped into the atmosphere. On the right is Gonglu's TIE GCM simulation, the same model we showed before. And it's showing the modeled response of the neutral gas to that energy input. And again, you can see very similar to what we saw before. You get these very strong wave-like variations where you get local heating, and those heating pockets of the hot gas, they generate wave-like disturbances that propagate to low and mid latitude and really just modify the whole atmosphere, not just the high latitude region. So we want to understand the left-hand side, which is how are the energy inputs distributed, and the right-hand side. In particular, on the left-hand side, you can see what we have to do typically is we have to use a single satellite to understand what the high latitude forcing is. We combine that with ground-based measurements of magnetometers and radars and things, and we use that to deduce what the energy inputs are. So one of the things GDC is going to do is dramatically improve our ability to specify and constrain the high latitude energy inputs, the electric and magnetic fields, the field line currents, the conductivity, and so on. And it will do that over a range of scales from hundreds of kilometers to the global scale. On the right, GDC will dramatically improve our ability to understand day and night, neutral density variations, neutral wind variations, neutral composition variations at very high resolution on a global scale. And that's why we're excited about GDC. Just for reference, just for completeness, I've included some of the lower atmospheric forcing. And this is simulations, high resolution WACM-X simulations from Hanli. And Hanli has developed simulations that show the propagation of lower atmospheric disturbances to the upper atmosphere. So you can see four levels of his model here at 11 kilometers altitude, 37, 87, and 100 kilometers. And because the density is falling off, the amplitude of these waves grows exponentially with height. And what start as small fluctuations at low altitude become very large and very widespread and large amplitude fluctuations right at the base of the ionosphere. And that's critical because those fluctuations can change the neutral atmosphere directly, and they can also change the electric currents that flow in that region. And that can generate electric fields, which can change at even higher altitudes, can modify the plasma distribution dramatically. So dynamic is really focused on this aspect, which is how does the lower atmosphere drive the upper atmosphere? GDC will be partnering with dynamic to make those measurements. So I wanted to sort of show the value of comprehensive measurements here. And this is why I say sometimes when we make sort of one measurement at a time, we measure the magnetic field only, like ampere emission, or we measure auroral emissions only by like the image mission. You get a great picture of what's happening, but you can't always understand exactly why something is happening. And so what I've shown here, just for analogy, is the stratospheric and tropospheric weather, in this case, the tropospheric weather in the United States for the same day, January 31st, in the year 2018, and then 1 year later, 2019, at the same time of day, 7 o'clock in the morning. And even though it's the same day, same amount of solar insolation, same position of the Earth in its orbit, the temperatures are dramatically different. And so if all you had was the measurement of the temperature, you'd be able to say the temperature variation is large and it's uncorrelated with, to some extent, there's variability that's not explained by solar insolation or axial tilt or position to the sun. If you then measure the pressure contours, you can start to understand it. You can say, okay, if we measure the pressure or the corresponding wind that's created by the pressure, we can say we have these red arrows, which are the winds that follow the ISO contours. And in the top case, where the winter is warmer, the winds below the jet stream blows basically across a line of latitude. And it doesn't really change the temperature very much. In the bottom case, what you're doing is you're getting a deformation of the jet stream that brings Arctic air down across the United States, dramatically lowering the temperature by 40 or 50 degrees Fahrenheit. And so if you just have the temperature, you see that there's a variation. If you have the wind and the temperature, you say, okay, there's a strong correlation. The wind is doing that. And you can predict it even. You could say if the wind looks like this, the temperature is going to be colder. The next step of questioning, though, is what drives the winds. And this is really what we want to do. We want to be able to take comprehensive measurements that show you the temperature and the wind variation. We also need to do it around the world in multiple spots, and I'll show you an example. In this case, the reason those winds do that is the polar vortex breakup, which doesn't always happen, but every so often in the winter in the northern hemisphere, you have the strong polar vortex winds that become unstable for various reasons. When they become unstable, the cold air that they normally trap over the poles can then be free to expand southward and modify the wind pattern and bring cold air over the United States and elsewhere. So in order from left to right, you have sort of different levels of understanding. How does the temperature vary? How do winds drive the temperature? And really, why are the winds changing? That's sort of the three questions you can ask. And I think GDC is really going to take us we're kind of in between the first and second stages of this discussion. And I think GDC is going to be the first mission to take us across to the next question, is why does it happen? And that's something we haven't been able to do because we haven't had the comprehensive measurements at the multiple local times and longitudes at the same time. So GDC is going to measure, again, the electric and magnetic fields, the energetic particles, and the currents that are going to provide the driving energy inputs from the magnetosphere. And it's going to do that at high resolution. It's going to do that characterizing instantaneous gradients. It's going to characterize the small regional and global, local, regional, and global scale, and the full range over a wide range from quiet time to active. That's very exciting. And then it will also measure the responses of the ionized neutral gases. This includes the bulk motion of the neutral gas and the ionized gas. We call this the wind or the drift. The temperature of the electrons, ions, and neutral gas. The chemical composition at very high mass resolution, very high precision of the neutral gas and ionized gas. And critically, we're going to have the first time a complete characterization of the spatiotemporal scales of the full range of IT responses, and that will include the first ever global wind patterns measured in space. Why are winds so important? I mentioned before that winds really, they can move gas around, they can transport energy through the system, they can transport energy from the magnetically closed region, high latitudes, across that boundary to affect the low and mid latitudes. And our current state of knowledge is limited. It's basically consists of some really recent measurements in the low latitude region of ICON, which has been groundbreaking, very, very interesting, that shows the lower altitude winds. We have ground-based measurements at nighttime from a number of stations, but they're not uniformly positioned, and they only measure at night when there are no clouds. And then we have one other major mission which provided wind measurements, and that's the Dynamic Explorer 2 mission in 1982. So it's been 40 years since we've had in situ measurements of winds on the Earth. And you can see how the wind changes here. This is an example of 1 day of measurement from Dynamic Explorer 2 on the right. And this is a period where the IMF turned southward and started dumping energy in. So the first 3 vertical lines below this, the yellow ones, those are the horizontal wind vector as the Dynamic Explorer goes up over the pole and through the high latitude region. And for the first 3 passes, the solar wind is quiet, there's not much energy being dumped in, and the wind is relatively small and relatively quiet and relatively consistent from pass to pass. There's some small differences as we go. Once the IMF turns southward, almost immediately the neutral winds respond. And they become very large, and they become very dynamic. You can see the changes from orbit 7214 to orbit 7221, 7 orbits later, just about 10 hours later, the wind is dramatically different. And so this is the tantalizing evidence we have of these neutral wind variations. Dynamic Explorer had only an 18-month lifetime, and of that time, it only measured neutral winds part of the time. For example, here you can see that it only measured every second or third orbit, so every 3 hours to every 4.5 hours, depending. It was making a single pass with a single spacecraft. So it was tantalizing. I say we learned a lot about what could happen, what possible could happen. We learned a lot about the potential correlations between neutral wind and ion drift, but I think we didn't ever get a proper picture of how the winds vary and why they vary. So we want to understand, what are the coherent wind patterns and how do they evolve? How do the winds transport different chemical species? How do the winds drive momentum exchange and heating with the ionized gas? And how do winds evolve in time and what drives that evolution? So you can see here, just sort of picture, this is a picture that shows in blue arrows the plasma motion in a model. This is, again, a CTIP model by Tim Fuller-Rowland. And the red arrows are the modeled wind. And unfortunately, it's in a frame that's co-rotating with the Earth, but you can kind of see the wind and the plasma drift do not flow in the same directions. They have different structures. They have some structures where they can affect each other and become similar, but in general, they are different circulations. And so these are model efforts that we have based on our best understanding, but no systematic, sustained global measurements have ever been made in order to confirm or test these and other predictions and refine our models. So we want to understand these winds. We understand the drivers. The winds are driven by pressure gradients when you heat the gas in different regions. When you have ion drag, as the ions are dragged by electric and magnetic fields across the neutrals, they can exchange momentum with the neutrals and accelerate the neutrals. You can also have neutral drag and viscous forcing. Then you can have Coriolis forces. And if we have those four forces together, we can deduce how the wind is going to change. And I put in the upper right a picture of what GDC Constellation will look like during part of the mission. And you can sort of see the beauty of this. This is each of those colored lines, there are 6 of them, shows one of these satellite orbits. And they're roughly spread evenly in local time at that time, not exactly. But you can imagine now crossing through that complicated pattern on the left, you'd be able to deduce how many cells there are, where the cells are located, what their strength is, what their intensity is, are they twisted, and so on, by making measurements appropriately distributed in local time and longitude and latitude. Okay, so this is the rest of goal 1. We have 3 objectives in goal 1. As again, how does the high latitude ionosphere thermosphere respond? In the first case, we study the neutral wind. We try to understand what drives the neutral wind. And again, there's model elements there. You can see of the plasma circulation on top from Yue Deng and Aaron Ridley, and on the bottom, the model neutral circulation. And we really want to really test and explore those simulations and those theories. A second one of high interest is the development of high latitude plasma density structures and how coherent structures are formed and evolve as they move across the polar cap. So these are polar cap patches, typically so-called, that basically form from the dense dayside plasma. Reconnection then can sort of section off a piece of that, some of those flux tubes, and send those and train those flux tubes in the cross polar cap convection, and they evolve. They become they modify the neutral gas, and they modify their own conductivity and the heating rates as they are convected across through the background neutral gas across the polar cap. And they can cause, from a standpoint of space weather, they can cause scintillation and effects on radio wave propagation. So understanding what drives those polar cap patches, how they break off on the day side, how they are tracking through the convection pattern, and how they evolve in terms of developing instabilities or changing their spatial structure as they move across the cap is of high importance. And then the secondary part is how do they impact the background gas? Because as they're moving, they're changing the Joule heating rate, they're changing the conductivity, and so on. And that can be a major impact. So we want to understand the causes and consequences of those plasma density structures. The top right picture shows the neutral density variation. This is a nice picture from Liu et al. That was developed from many months of, I think in this case, swarm data, could be CHAMP data, I forget. And they just show the deviation of neutral gas from the average or from the model. And you can see these percent differences there between the quiet and active time. You typically have a large density enhancement that's more or less persistent in the region of the cusp. You have some night side enhancements. And these density enhancements, again, they modify the Joule heating rate, they modify the conductivity, they can modify the chemical recombination rate of the ionosphere and change the plasma density, and they can have impacts on space weather issues like orbital drag and satellite motion. So understanding what causes these neutral density enhancements, there's a lot of controversy right now as to whether they're caused by small scale field line currents, filamentary currents, versus soft electron precipitation, or versus wind divergence that can, or vertical winds. So there's a lot of questions we have about what makes those, and I think GDC will contribute quite a lot to that. Our second goal is also very interesting. I put the 4 objectives here. We have these are all about how the energy, mass, and momentum get transferred to the low and mid latitudes. The top left is really about high to low latitude plasma coupling. So we know there are many mechanisms by which that can happen, but 2 of the most interesting are the disturbance dynamo. When you put energy in the aurora in the high latitudes, that heats the gas, the neutral gas, and that drives wind equatorward. And that wind modifies the normal wind. And that normal wind is what drives the electric dynamo that sets up the electric field and the plasma motion. If you modify that dynamo by changing the wind pattern, changing the pressure gradients, you'll change the current systems, you'll change the electric fields, and you will drive plasma in a different way than it is used to doing during the normal quiet time period. The disturbance dynamo is a process that requires that heating and that transport over several hours towards the equator. The other way you can get interaction is by direct electrodynamic interaction. And so typically the ring current and the intermagnetosphere, or the region 2 currents, shield the low latitude regions from direct interaction with the solar wind. But for rapid variations, ones that are happening faster than the shielding currents can adjust, you can have that electric field propagate directly down to the equator. And so you can get very rapid variations with very quick response time. but they tend to have a decay that's a little bit different. So one of the things we want to do is understand when we see these variations, when the plasma density suddenly becomes uplifted at the equator, we suddenly get changes in the plasma density. We will measure the electric field that causes that in the plasma motion. And we'll also try to understand what changed the electric field. So it's sort of that next step. How does the plasma density change? What is the electric field that made it change? And then, but importantly, where does the electric field come from? Is it disturbance dynamo? Is it penetration field? Is something else happening? So that's objective one. Objective two is propagating atmosphere and ion disturbances. These are TADs, traveling atmospheric disturbances, and TIDs for ionosphere. And these are either small, medium, and large scale wave-like phenomena that can propagate for very long distances. And they have interesting space weather implications. They can also transmit energy momentum across many degrees of latitude. We understand how those two are connected, how the atmospheric disturbance and ionospheric disturbance are connected, how they evolve as they propagate, what drives them, and so on. The third one is composition changes. We really want to understand how do the chemical composition change. And again, this is an effect that we think happens when the high latitude regions are heated. The heating goes deep in the atmosphere and causes a lot of upwelling of heavy molecular nitrogen, N2. And that N2 has different effects, different mass, different chemical reaction rates, but it gets lifted to higher altitudes. And in particular, the N2 is good at catalyzing recombination of plasma. So in regions where you have enhanced nitrogen, you get reduced plasma density. And it's an observation that this region of higher, richer nitrogen gas or depleted oxygen gas tends to start at high latitudes and propagate equatorward, again, in a similar way to the disturbance dynamo. We don't understand exactly how that happens. And then finally, one that's kind of recently topical, is hemispheric asymmetries. We know that typically the hemispheres are, if they're in solstice conditions, one is going to be summer and one's going to be winter. But there are other interesting differences, like the land-sea difference there, and also the offset of the magnetic pole and the higher order than dipole moments in the south, and so on, different magnetic field strength. There's enough differences there that you really want to understand. For the same, say, time of year, even for an equinox condition, there will still be differences in Poynting flux and conductivity and plasma neutral motion, ionized motion. We want to understand those by having satellites measure at the same time in both hemispheres. I think that's very important. Those are our objectives. I won't go to this, but I want to now say, okay, now we've got our science that's been laid out. If you have any questions, please ask me. I'm running a little bit long, so I want to get through this next part for you. But please do interrupt if you can. In order to understand those phenomena, we have 6 instruments on board, and these instruments measure, again, all the different critical state parameters, the energy inputs and the responses. And just show you here what they are, we have a ether instrument led by Professor Lila Anderson at University of Colorado, LASP, and that is a Langmuir probe system to measure electron temperature, plasma density, and small-scale density structures. We have the CAPE instrument, which is a top hat analyzer. This is led by Dan Gershman at NASA Goddard, and it measures the energy pitch angle distribution of electrons up to 30 keV and ions up to 40 keV. It does not measure composition of ions, but it measures the energy spectrum and pitch angle distribution. We have the profile instrument, which is led by Olga Verkhodliadova at JPL, and that is a radio occultation instrument, familiar to those of you who worked on Cosmic 2. GDC will be the lower altitude than Cosmic 2, so it's a very capable instrument, but there will be some measurements that we can make with Cosmic that we will not make with GDC, just where it's so low in altitude. In particular, some of the full altitude profiles will be very difficult to get, I think, from GDC standpoint. We will be able to typically measure the height of the F2 peak or the F peak, the number density there. The vertical TEC will be very interesting, scintillation, and we'll occasionally get altitude profiles as well. So I think this is a very exciting opportunity to provide complementary measurements to Cosmic 2, I think. We have the Mosaic instrument led by Mehdi Bennett at the University of Maryland, Baltimore County. That is probably the most most capable mass spectrometer that's been flown in 40 years at Earth. It's very similar to the MAVEN NGIMS instrument, for those of you familiar with that one. It measures, its primary purpose is to measure the chemical composition of the ions and neutrals. But with careful modulation of the incoming flow by either retarding grids or by moving baffles, they can deduce the incoming angle of arrival and the energy of the incoming gas and thus get a three-dimensional wind or drift vector and temperature, as well as the chemical composition. Very capable instrument. It has 1 AMU mass resolution and can separate even very slightly different species with chemical precision. It's very sensitive as well. So I think that's going to revolutionize our understanding of the atmosphere. We have the TPS, a thermal plasma sensor. This is, again, an instrument with long heritage. This is produced by Professor Phil Anderson at the University of Texas, Dallas. And this is similar to the IVM instruments that are on board the Cosmic 2 satellites that flew on ICON and that have flown on a number of satellites for the last 60 years that measure the ion drift velocity, the density, and temperature. And then finally, we have the Nemesis instrument. This is led by Professor Mark Moldwin at the University of Michigan, and it's a vector magnetometer, a flux-gate vector magnetometer. Again, I can leave these slides with you if you prefer, and you can look at these tables at your leisure. But these we're going to be publishing a paper on GDC by the end of the year, and it will have these numbers there so you can reference them. But this is the expected performance on the instrument measurements. We have these 14 physical parameters that range from thermal ion velocity, thermal plasma density, and so on, neutral gas, etc. And you can look at those, and you can see what the dynamic range we expect to measure is, what the accuracy and what the precision is, and also the sample rate. And so typically we're measuring things approximately once per second, but we might have a few cases where we measure things with higher resolution even. So once per second is about an 8-kilometer sample cadence or 16-kilometer spatial resolution. What I want to get at is some of the benefits of using multiple spacecraft. And so this is just an example I worked up again using stratospheric and tropospheric weather as an example. On the bottom right is the actual thing that's happening. And this is an actual image of mesoscale convective system over the United States. And this is water vapor images from GOES-13. And you can see over time, something that has a lot of spatial structure, a lot of temporal variation. And if you had the way to image it, as they do in this case, you'd be able to really diagnose and deduce what's happening. In the top left, I show what happens when you only measure in situ measurements, when you only measure the local measurements along the track. You only do it with a single spacecraft, which makes a single cut in longitude. It cuts through in a single longitude, cuts through in latitude. And then it does it every 90 minutes. And I just took a sort of a scale size here. You can sort of see if all you had was the information on the top left, basically what I've done is blacked out all the other picture in the bottom and only updated every so often. You can see that it's very difficult for you can tell that there are variations there, but it's hard to say, do the variations moving in and out of the frame? Are they growing in situ? Sometimes the variations vanish from pass to pass, so you can't watch them evolve and change. And so I think it's very challenging sometimes, depending on the time scales and spatial scales involved. It's very challenging to use a single satellite in situ to look at complex systems, especially if your visit rate does not match well to the evolution time. You could do something a little bit better, which is if you had more than one spacecraft, so say in the same orbit. So single spacecraft with rapid revisit time. The top right shows the same slit, kind of looking at the same picture, but updating more often. Say if you had 2 spacecraft in the same orbit or 3 spacecraft in the same orbit, you still can't sort of see what's going in from the left and right, but maybe you can catch the same phenomena with 2 subsequent measurements and watch it evolve in time. So that's an improvement. So the first picture tells you what types of variation exist. You can average your data over many, many days and months and try to get an average picture. The second one starts to tell you how does the weather change in time, but there's still a lot of questions. When you do the following, which is to have multiple satellites, you can sort of see it starts to approximate with a real ideal picture. You still don't have everything. You still aren't capturing all the small scale structure, not capturing the fast time variation. But you can, depending on how you structure your mission, you can start to get enough information to really come and answer a lot of the questions. Why does the weather change the way it does? I think here you can see that there's a swirling hot spot that's rotating as it grows and moves across from west to east. You can see the outer bands of clouds. I'm not a meteorologist, but you can sort of see all these different features, and you can reconstruct a lot of what's happening in that cloud and storm system. So you don't get everything, but you can sort of see the power of having multiple spacecraft. The way we use the multiple spacecraft is just conceptually we have 6 spacecraft, but you pick any 3 of them, that's sufficient to measure an instantaneous latitudinal and longitudinal gradient. And as soon as you have a 4th or more spacecraft, you can start to revisit the same region and get time variations. And so we have available predicted ephemeris for the entire 3-year mission, and that's publicly available. You can see that link there under this QR code. And if you search for GDC ephemeris, or if you email me, we can also send it to you. We have basically at 30-second resolution for 3 years, every satellite's latitude, longitude, and so on. And you can sort of follow the satellites, see how the constellation evolves, and see how it might fit in with your research. We plan to update this and revise it a little bit, and we are looking for input from the community, from the international community, about how could we optimize it, how can we make it better. So I recommend that you download those and sort of examine them. There's a document that goes along with it that tells you what the files mean, but there's also just data files of each satellite for each year of the mission. The top right shows the result. So if you take those individual triangles and you sort of figure out, then if I have another triangle, you have a single triangle that occupies a certain region, another triangle comes by at some later time. You can say, now I've got a spatial scale defined by the size of the triangle, and I've got a time scale defined by how much later in time that second triangle occupies the same space. And what I've done here is I've shown what is the distribution of those spatial and temporal scales that GDC will measure. If you look on the vertical scale, that's the scale size on the logarithmic scale, and sort of goes from 50 to 12,000 kilometers. And the horizontal axis is the delta t, the revisit time, from 60 seconds to half an orbit. And again, because it goes to half an orbit, then we wrap around, and you can imagine we can measure any time variation because there will always be some way to measure them with this setup. And then the color shows on a logarithmic scale the number of hours that we expect to spend in that configuration. And you can see we get a lot of coverage in the 1 to 5 minutes sort of time scale. And we get most of our coverage there from 300 kilometers to several thousand kilometers, to 10,000 kilometers. When we get out to longer time durations right now, our current scheme, we really only measure those at say 1,000 kilometers and larger. We don't look at like 10-minute variations or 50-minute, 30-minute variations. We do that at kind of 1,000 kilometers and larger. We're exploring whether we can do that with smaller spatial scales to try to fill in more of that gap there. But there will be scales that we can't reach with GDC. But one of the questions we have as we refine our ephemeris is, can we improve this further and kind of get a better distribution of coverage versus spatial temporal scale? But I think we're capturing a lot of interesting dynamics, and dynamics that we've never been able to do before. We've never even had the 5-minute scale before, much less the 300-kilometer scale or any of these other pieces. So I think if you were to look at what we've measured in the past, having full horizontal gradients and time gradients on all these scales is extremely unique, and I think very exciting about GDC. How do we do that? We have 6 spacecraft and we launch them as single orbit plane. And if you download the ephemeris, you'll see that. You can sort of see we launch into three slightly different inclinations, like 81 degrees, 81.5, and 82. And then in those 3 inclinations, there's a pair of spacecraft in each. We then use small burns from the onboard propulsion to, again, slightly adjust their inclination even further to get 6 orbit planes. Those 6 orbit planes are very close together, but they're very slightly different inclination. And so their local time, the ascending node precession rate is different. And it's to the point that they spread out slowly over a, say, 2.5-year period. They go from being almost co-located to basically covering all local times. So about 2.5 years to do that. In the process, they start close together. You can see the bottom left. This is sort of a case when we're saying a local scale, several hundred to several thousand kilometers. And you can see the 6 spacecraft there are sort of in hexagonal shape, and that we call that our MOB. It's our multiple overlapping baselines, because each set of 3 spacecraft gives you a spatial gradient measurement, and we have 20 triplets that we can make, independent triplets we can make using those 6 spacecraft. So there's a lot of overlapping baselines of different scale sizes, and you can use it to really constrain the spatial variation. We also have in the top right we call it follow the leader. And I don't know if you can see it, but if you look carefully, you can see one set of 3 spacecraft coming up and another set of 3 spacecraft following, say, a few minutes later. And the purpose of that is to get those longer time revisits where you can sort of study a region and then pass through. There's a region passing through the high latitude region, and there's another one right there following behind it. So you can kind of see those two groups of 3 following after each other to kind of get those longer time variation measurements. Over time, those orbit planes spread out further, and we get into regional mode, and then finally the global mode. And you can sort of see the global scale is the middle bottom panel and the right bottom panel in different projections. You kind of see the local time variation there is pretty even across all local times. And then on the right, it shows you what it looks like in a latitude, longitude, Mercator projection. So, yeah. We've also designed it so that we can be robust. If we lose any single spacecraft, that we can still achieve our mission, and any 2 can achieve the threshold mission. the beauty of that is we can design spacecraft that are only single string and don't have lots of redundancy, which makes them expensive. This is how the geometry looks in detail. If you were to follow the 6 spacecraft, this is at 3 different phases of the mission. This first top row is the early phase, the local phase, when the spacecraft are close together. And what you're looking at is a northbound pass close to the equator on the left-hand panel on the top row, and getting progressively closer to the maximum latitude on the right. And the dotted lines show the future trajectory of each spacecraft. So you can sort of see like the green dot would be spacecraft, say, number 2, and the green dashed line tells you where it's going to go in the future. So it gives you an idea of the sampling geometry. What you can see is as they reach the poles, that longitudinal separation becomes narrower as the orbits kind of intersect near the poles. So you can kind of see what happens there. We've drawn a blue line when we think we have a high quality sampling geometry. And you can see very near the poles, it almost becomes a string of pearl situation. So that might be very interesting for other science. If you want to look at rapid time variation, you can do that with this configuration. And the middle row shows a later time when we're spread out a little further. And the bottom row shows when we're close to the global phase, how the geometry looks. One of the techniques, we have several techniques we're developing, and this is another area of collaboration we'd like to learn from what everyone here has done for different reconstruction techniques. And there's been a lot of work done on Cosmic 2, but also many other science topics. One of the topics we're using, this is a paper developed for the cluster mission by Johann de Keyser, and it's a least squares method that sort of optimally combines data from these multiple spacecraft sampled over time to try to reconstruct spatial and temporal variations. And this is work done by Hassan Akbari, who's a talented scientist on our team. He has developed and programmed this algorithm and been testing it to take simulated GDC data with noise, fly it through sort of arbitrary distributions of density or temperature or electric and magnetic fields, and then see with what error bars we can reconstruct the original and sort of understand when the techniques work and when they don't. And he's done a lot of work on this. This paper is in submission and we publish soon to kind of show some of the new techniques we can use based on what we learned from cluster and swarm and other missions. How do we use these 6 spacecraft to their best advantage? And this is not the only way. There are many ways we will analyze their data, but this is a particularly interesting way in my view, because now you can measure the actual density and the gradients in the density and the time variation with some decent accuracy. One of the other things we're very excited about is the opportunity to work in conjunction with ground-based observations. I think the ground-based observations in particular would be of very high utility to GDC, and vice versa. I think GDC can provide useful constraints. If someone is studying using a very sensitive ground-based technique to study some aspect, having GDC fly nearby or fly over the measurement will provide lots of great correlative measurements for most studies. So I've shown here just a couple examples that, ISR radars are very high value. We have in the bottom left some scanning Doppler imagers. They're basically Fabry-Perot measurements of the neutral wind and temperature there on the bottom left. We have all sky imagers in the center bottom, which is an example from another event near Svalbard. And then we have magnetometers, we have rheometers, and so on. And I've just drawn some examples. They're high latitude examples of the northern hemisphere. But of course, we have those instruments everywhere. And I know that many people on this call are involved in, say, the International Meridian Circle project or a number of other projects that really are exciting ways to increase our global coverage dramatically and really get, the more measurements we have into the more conditions at different latitudes under different longitudes, we're going to do much, much better getting the most value out of the GDC science. So my colleague, Bea Goddard, she's working with us very closely, and she is the lead of the ground-based coordination for GDC. She has a group that meets regularly, I think once a month, and they welcome scientists from anywhere to call in and to propose different collaborative activities, or just to learn about GDC, or just to inform people about what you're doing. There's sort of a multiple purposes to that group is to learn about GDC, to express what you're doing, and then also to partner and plan some collaborations. We're hoping that GDC can be a nucleus by which people can encourage their own funding agencies to say, hey, I want to do this great thing. And it's even cooler because we can combine with GDC measurements. So that's why you should fund me. We're hoping that'll be an impetus for many people to develop funding in their health. If you scan that QR code, you'll be taken to a link that lets you sign up to get on the mailing list and get the calendar invitations for the ground-based coordination group, or you can measure Bea Goddard herself or me. Lastly, I want to just talk about the space weather briefly. This is actually very important. Again, GDC is not a space weather mission, but we hope that after GDC, we'll have a much better understanding of space weather effects. This is something from the APL gap analysis that shows sort of where different space weather effects happen. And almost all of them happen, the ones that affect us, almost all of them happen in the ionosphere thermosphere. And I've circled in red the ones that GDC will directly affect and measure. We'll measure, for example, the conditions that give rise to radio wave propagation and scintillation. We'll measure, we have a dosimeter on board to measure the radiation dose for aircraft at polar flights. We'll be measuring the orbital drag very explicitly and what drives the change in the orbital drag to help with satellite collision avoidance and space traffic management. And we'll be looking at geomagnetically induced currents, the forcing functions for those, the actual currents. You need to make measurements on the ground, but we'll be measuring the ionosphere currents that can give rise to those that affect power systems and pipelines. This is just an example. You know, we use these 6 observatories to provide the first global view of space weather in the low Earth orbit. But if you know, low Earth orbit is getting very crowded. You know, orbital drag variations that are not predicted in models, they can modify orbits unpredictably. And as we get denser and denser, closer and closer packed, that's a risk of collision, which can lead to a Kessler syndrome or runaway syndrome. And in particular, you know, we have this great rise of telecommunications constellations, going from the total number of active satellites in the world was something like 2,000 a few years ago, and now it's 4,000, and pretty soon it's going to be 43,000. So low Earth orbit is getting much, much more busy, and I think knowing the orbital drag is very important. You can see this affect the Starlink reentry by accident. They launched on February of 2022, and because of neutral density variations that were unpredicted, they lost control of some of their satellites and they re-entered much, you know, after a day or two of orbit. So GDC will help us to predict those conditions. I think I'm about out of time. I'm so sorry to keep running. I'm just going to 2 more slides and I'll be done. The real-time space weather, we are going to transmit real-time space weather. We encourage partners around the world to utilize this for their own needs and to work with us to make sure it's as useful as possible. Catherine Garcia Sage is one of my 2 deputies, along with Larry Kepko, and she's in charge of space weather for GDC. And I think she would love to hear from space weather researchers in your areas, and also from your nations, your space weather users or operational groups that would say, hey, if we only had this measurement, we could use that to drive our forecasting models. We use that for situational awareness. So we really want to meet with everyone and understand what would be the most useful. We will then provide real-time space weather. It will be low resolution, but still decent data, unique data, I think, at latencies of a minute or 2 and pretty high coverage from all 6 satellites. So that will be something we can provide to the world, and I think will be very helpful for everyone to better understand the space environment. Lastly, I wanted to show this picture because I think this is directly related to the reason I'm here is international partnerships are absolutely critical. The solar terrestrial physics, it's a global phenomenon. It's a global thing that we can't understand in any given country. No country spans enough geography and has enough people and has enough resources to solve this problem. So by combining data from everyone and using everyone's brain power, we can make much more progress. And so I'm just showing in NASA's picture is that we have this great observatory. We'd like that to be an international great observatory where there are different missions from all over the world. Cosmic is an important one that I unfortunately left off, but is actually critical for this. Dynamic and GDC form sort of a NASA strategic hub. Other nations will bring in their own strategic efforts. We'll have ground-based from all over the world. That's probably a really critical aspect. And then also important is the simulation theory and data analysis tools will be developed all over the world. And I think, again, our data will be open and free, and we hope that partners will also do the similar freedom of the data. And then we can all utilize each other's data to make the best impact and coordinate together. This came out of an effort called the ISTP Next. ISTP was the International Solar Terrestrial Physics Program, very successful international program that produced wind and geotail and polar and SOHO, and also the SuperDARN network and many other things back in the 1990s. And that QR code takes you to the ISTP Next report to understand how we might think about ourselves as a global heliophysics community. And if you have inputs, let us know on that. So this is the final page, and thanks again for your patience with my initial screen sharing. We're continuing development. There has been a little bit of slowdown in the budget. We hope the budget availability will increase soon so that we can progress towards the early 2030s launch. We do have money right now. We are working, and we're focusing on science instrument development. In fact, we're expecting to select our spacecraft vendor late this year. That's the last of the big procurements. And once we've got them on contract, we can really start designing and engineering and understanding the system. We know that GDC will partner with Dynamic and many others in the world to be the sort of hubs for the Great Observatory. But Dynamic is a particularly interesting mission that will measure the lower atmospheric forcing while GDC measures the main atmospheric force. And really, the most important thing I can say is we're really looking for global science partners, collaborative research tools, lessons learned and science learned from existing missions, synergistic efforts. If there's something you're planning and you want to maybe find the best way to optimize it along with GDC. And then during the GDC era, ground-based and space-based observations from other assets that can leverage GDC and vice versa. That would be very helpful. So I've included some contact information here, my name for general questions, my two deputies, Catherine Garcia-Sage and Larry Kepko. They're very well versed. You can talk to them directly about any question, but Catherine's particular specialty is space weather and Larry's particular specialty is international partnerships. And then Dr. Bea Villard-Lacourt is our ground-based observer coordinator. I recommend you talk to her if you have questions about that. And we have 4 QR codes on the bottom for our website, the ground-based coordination group again, the ephemeris download again, and a community Slack channel, which we will be using to communicate in both directions very well. Any questions? Thank you so much for your patience with the initial, and thanks for your patience through my talk. I appreciate it.
So thank you, Dr. Rowland, for the insightful presentation. So due to the time constraints, we will now open the floor for 1 to 2 questions. We are welcome everyone to turn on your microphone or type your question in the chat box. Anyone has a question? So maybe I have one question, quick question. So Dr. Rowland, do you believe that satellite constellation will be the trend for the future space mission?
I think so. There are problems that you can really do with one satellite with a big aperture. If you're studying the sun, you might need a big telescope. Certain problems in ionosphere thermosphere, you might want to have a really well instrumented larger satellite. But for many of the problems that we're studying, we need distributed measurements of these mesoscale and larger scale features that a single satellite cannot measure by itself. So I think the other way we can go is with imaging, of course, and there's different remote sensing techniques that can do the job. I think Cosmic 2 demonstrated the very high value of remote sensing, but it also demonstrated the high value of Constellation. And now we're getting, globally at 1 hour resolution, global measurements of the ionosphere, the complete ionosphere. And that's groundbreaking. And I think that really Cosmic 2, Cosmic 1, Swarm, Themis, these really highlighted the value of these multi-point measurements.
Thank you. So would you recommend the country, those with a limited budget, to focus on the development of the small satellite or the micro satellite?
I think there's many areas, and it really depends on what the science goals of each research group or each organization or each nation are. Almost anything is of very high value, to be honest. We have enough gaps in our observations. Small satellites are great, large satellites are great. Ground-based observations are very powerful, and I think really provide a really important context for all these measurements. And also, you do science that you cannot do with orbiting spacecraft that way.
Mm-hmm.
But also things like training scientists and being ready to access the data and use it when it's coming on board. That's a very valuable thing too. Many of our scientists on our team have worked on international projects or have come from other nations, and we benefit from the international community really providing strong scientists from everywhere, I think.
Yeah, thank you.
Thank you so much.
Sorry. Anyone has question? Okay, so it's about time. So if you have further question or the topic you would like to discuss with Dr. Rowland, please feel free to email us. We will pass it on, or you can directly reach out to Dr. Rowland. So we are deeply appreciate the presentation from Dr. Rowland today, and thanks for everyone for joining us today. We look forward to our next time online seminar. See you next time. So thank you, Dr. Rowland. Thank you. Bye-bye.